Alrighty, greetings from Mike's Custom Flooring from Redlands, California. Thank you all for joining us in person and those of you joining us online. Let me introduce myself really quick. I am Eric Esparza. I am the CEO of Mike's Custom Flooring, president, lead janitor, really. I'm really good at taking out the trash and cleaning the dishes because no one else does around here. But sometimes I come up with a really good idea, and that's why they keep me employed. And that really good idea, I think, is this concrete moisture emissions conversation. Whose fault is it? I know a few of you have had change orders or quotes for moisture mitigation in the tens, 20s, 30s, thousands of dollars. Sometimes these moisture quotes are as much as the install of the original material. And they're in slabs that are 30 years old, 50 years old. They happen in slabs that are just poured 6 months ago. They're in slabs that are in a barren desert. And you sometimes ask me why that's happened. And I don't know, we look around the building and we look for sprinklers and we're trying to find out, from just deduction of, our natural environment, why that's happened. And after seeing a presentation from George Donnelly a couple of months ago, I realized that there are some other factors that are involved, and that's what we're here to talk about. The reasons for those other factors, and possibly being able to mitigate these problems before construction starts. We give this pricing or these change orders to owners or board members or owner representatives in advance, not at the end of the project when you're trying to close out, you got one trade left and they hit you with a big change order. So MCF has hired resident expert George Donnelly. George has about 40 years of experience in the floor covering industry, from technical support in vapor control, concrete. He's a member of the ASTM, ACI, and a bunch of other acronyms that make him smarter than me. And we won't go to all that length, but so sit back and enjoy. I think that this conversation, I want this to be a conversation, not an educational seminar. This is something that I'm hoping, if you have any questions or if you think that something that George is saying is kind of BS, raise your hand. Let's talk about it. I want to get everyone on the same page, from my employees, the customers, to owners, on the same page about why moisture is happening, how we can mitigate it before we start construction. So at this point, George, take it away.
Very good, thank you. Appreciate people being here. I'm not going to bore you with a lot of detail. Eric touched on it. I've been at this a long time. I've had this business for over 20 years. And in those 20 years, I've been a member of ASTM Committee F6 on resilient flooring, which has written the standards for moisture testing that we're going to talk about. I've been a member of ACI Committee 302, concrete slab and floor design and construction for that same length of time. I'm also a member of the International Concrete Repair Institute. So that only means that I get to sit through meetings and learn from other people who know a lot more than I do in many cases. The objective here, of course, is to prevent floor covering failures. Eric was touching on the idea that change orders are ugly, and certainly they are. I don't usually get involved in change orders. I get involved in failures. And when I see failures, and I can think of some in Southern California, where the remediation because of downtime, moving materials, etc., was no longer the $4 or $5 a square foot, but ended up $100 a square foot. It's the failure that's horrific. So remediation is ugly, but failure is unacceptable. So we are going to go through this, and questions are welcome. If I think that it's something I'm going to touch on, I may put you off for the moment. But if it's otherwise something that has to be addressed, we certainly want to do that. So I think we can look at it as, why are we here today, and can modern floor covering systems and concrete floor slabs peacefully coexist? And to some degree, will you be held responsible if they don't? And that responsibility can fall to a general contractor, a flooring contractor, a concrete contractor. And in many cases, I've actually sat in mediations and arbitrations where we looked at an architect and said, you designed something that couldn't possibly work. So there is a whole chain here. And if we take that hypothesis that moisture and alkali passing from or through concrete floor slabs is responsible for countless floor covering failures, then the question begs, is it the floor covering and our floor covering system failures the fault of flooring or coating manufacturers, which frankly a lot of people would like to believe. So I'm not going to spend a lot of time on it, but just some of the failures that I've dealt with over the years. And I could show you thousands of pictures that's worthless, but at least a few. This was a solid vinyl tile. This was a new construction, was in fact in California. Months after move-in, there was oozing at the tile seams. We picked up the floor tiles and the adhesive had completely emulsified into a liquid milk. We see carpet tiles where we have condensate liquid underneath those carpet tiles. Certainly that's not an acceptable situation. This was also a new construct. This was in California. This is a clear epoxy coating in a shoe store, and the epoxy was blistering. We chipped up the epoxy and there was liquid condensate, which dried pretty quickly, but liquid water had collected underneath that epoxy film. Another one, these are some of the more horrific failures. This is VCT, new construction. And again, adhesive is virtually completely dissolved into a milk. This also California. This was a plank vinyl top, vinyl bottom with a real wood veneer inside. Moisture coming up was discoloring the wood at the edges and seams. Not an acceptable situation. Rubber flooring is always fun because we're often installing it with an epoxy. So the epoxy holds pretty well, except in areas that are weak. We end up with blisters and bubbles. And if we poke one of those bubbles with a pin or a nail, we'll typically shoot water 2 to 3 feet in the air, and that always excites people a lot. Another VCT, and this was a distress for me because this was housing for the elderly, again in California, probably 9 months after move-in. And my concern was not the floor failure, but the amount of moisture and the other things that were being affected to where health was really the issue, not the floor coverings themselves. So there's always more than just moisture and floor covering at issue. If we have that kind of intrusion, we're worried about mold growth in walls and on furniture and clothing. But it's not always just new construct. Remodel, as Eric alluded to, can be just as big a problem or a bigger problem in many cases. This was a lab. VCT had been in place for 25, 30 years, and they said, well, we're just going to go over the top of it because, heck, it's been there, it's down flat, and everything's wonderful. Went over the top of it with a water-based adhesive where the original tile was held by a solvent base. And at the seams, we now had moisture oozing up between the tiles, dissolving that adhesive. This was literally just weeks after installation. And that arrow was pointing to actually liquid ooze coming up between those tile joints. And of course, that liquid passing from or through concrete is going to be at a pH of 12 to 14. So it's going to dissolve the adhesives that are sitting there. Probably one of the oldest pictures that I'm aware of floor failure. This is actually a picture taken by Peter Craig, whom I've worked with on a number of projects. And this was a situation where we had solvent-based cutback on the concrete. We had a VAT tile down for years and years and years. People said, we don't want to go through the asbestos abatement. We're going to go over the top of it with a VCT. Of course, it was held in place with a water-based adhesive. Just months after installation, we had complete emulsification of that adhesive and a total loss of the floor. And now we did have to demo all the way back down to the concrete and start over after a mitigation system was introduced. So the remediation was really expensive in a case like this. So we look at those pictures and then the question begs, did the slides show floor covering failures? And I would arguably say the answer is no. The floor coverings, adhesives, and coatings were subjected to conditions they were never intended nor capable of dealing with. So the floor covering systems failed the owner's intended use, that's without question, but in fact, the concrete was either too wet when the floors were installed or became too wet sometime after installation. And that's what we've got to start looking at and trying to address. Before I talk about concrete, I think it is worth spending some time talking about modern floor covering systems and the evolution that's happened versus a revolution of what's changed. And we can start with looking at asbestos. We started phasing that out in the 1970s, and people assume that there hasn't been asbestos in flooring for a long, long time, when in reality, it was only outlawed at retail in 1992. So in 1992, we could no longer sell the product, understanding that some manufacturers started taking it out of product in the 70s, expanded in the 80s, but in fact, it wasn't until 92 that it was illegal to sell at retail. It's also noteworthy that it was California's South Coast Air Quality Management District that was the first to regulate the off-gassing of volatile organic compounds from paints, adhesives, and coatings, and that started in the early 1990s. But if you followed it, this is really where evolution versus revolution comes from, because those regulations have been ever changing. What was allowed even in the early 90s is certainly not allowed today. Our VOC off-gassing is much lower. I think they're down to 50 grams per liter, and we have a lot of products that are 0 grams per liter on the market to meet those requirements. But it wasn't until the early 90s. And in fact, in the early 90s, I was the technical manager for a distributor in California, and immediately our phone started ringing as adhesives were reformulated, with people saying, hey, I didn't have any problem with this adhesive just a year ago. Now I'm using this adhesive and it's no longer holding. Well, many manufacturers didn't change the part number of their product, but they did reformulate what was in there. And in fact, it was no longer working because we had to remove the guts from the adhesives. The other thing I've put on this slide, and again, it's just a matter of information, and I think it's important, particularly to generals who do remodel work, is that ASTM E1745, which is our standard specification for a subslab vapor retarder, was originally published in 1996. Prior to that, we had some generic specs for plastics, but we didn't have something specifically intended for a subslab vapor retarder until 1996. So I think that's an important number to keep in mind when we're dealing with buildings constructed in the 80s or 70s or 60s, likely don't have a vapor retarder that would meet this standard because there was no standard to try to meet. Looking at some of the issues then in unintended consequences, and in resilient flooring, permeability. The loss of asbestos has been a problem. When we look at those older products, whether it's a VAT tile or the very old 9x9 asphalt tiles, or the asbestos felt backings on things like Armstrong Coralon, these products were relatively permeable. So we could have concrete that was passing moisture, but the product itself was also passing moisture. And as long as the product could pass as much as the floor covering, we really didn't have a problem. So the loss of asbestos was part of the change in permeability of resilient flooring. But the other one that's not talked about enough, and I think is critically important for discussion, is the recognition that while designers may love all of the choices they have in texture and color and pattern and the ambiance they can create, one of the #1 drivers of manufacturers has been the demand of facility managers, for products that were readily maintained and hard to stain or soil. And virtually every resilient manufacturer, and I'm going to say the same thing about resinous flooring manufacturers, has responded in the same way. They've tightened the surface matrix of their product so that it was very difficult to stain or soil. It's been successful. But we have to recognize the converse of that. If nothing gets into these products, nothing will pass through these products. So in a nutshell, I'm saying we're now creating products that are almost perfect vapor retarders installed on top of concrete slabs. And of course, we're going to say that they're now held in place by water-based adhesives. So we've created an exacerbation of a problem by having a product that serves one need, but creates a problem in and of itself when we're dealing with concrete, which is made out of water. So we look at carpet. Again, when we talk about permeability, our old action-back carpets, our jute-back carpets, highly permeable. But when we went to vinyl backings, whether we're talking about carpet tile or 6-foot wide sheet, very high performance, so they're great products, but the permeability has diminished dramatically. And I can't tell you, because I'm talking to people from California while I was there, how many times I'd get called out to a facility and they'd say, well, we're having problems with the resilient floors, the VCT is curling, the sheet vinyl, the seams are splitting, there's moisture ooze, but our carpet areas are fine. And it was broadloom carpet. And I'd ask to walk the facility, and I'd do that, and invariably we'd find some desks with plastic chair pads. Pick up the chair pad, that carpet was soaking wet. Now we had a potential health issue because we had mold growth and fungal growth inside that carpeted area, which was a potential health threat to the employee. And again, it was the carpet that was freely breathing that allowed the moisture to pass through, but where we trapped it, we had a problem. Now, we do see some, well, again, I'm just saying it there. The broadloom carpet is permeable except for the chair pads. The next one, I was thinking I had included it in here. We're seeing some new carpet tile offerings with manufacturers that are claiming permeability of the product so high that you don't even need to do moisture testing. And while that is interesting, and I'm not even going to dispute that they've come up with products that are highly permeable, the problem still becomes the use of chair pads, problem with flat-bottomed case goods, and walk-off mats. I've already been called out to claims where, again, manufacturer said you don't even need to test the moisture in the concrete slab, just put down our product with tabs. And we go out, and here are areas where we have condensate water underneath that carpet tile, where there was a chair pad or where there's a walk-off mat. So it's a great concern, and manufacturers in many cases are making claims that are a disservice to the end user, and then in turn the architect, general contractor, and flooring contractor. So if there was a manufacturer on, I'd be happy to beat up on them, because they're making claims that are unsubstantiated and or at least misleading. When we talk about the issue of unintended consequences, again, adhesive systems, so we removed the solvents, and that's been a good thing for indoor air quality. However, we've replaced those with water-based carriers and sometimes organic fillers. My concern about the organic fillers is for fungal growth, that's called food. So it only takes a few things to cause fungal growth. We have to have spores, which I guarantee you, even in California, are in the air all the time, all across the state. We have to have moisture, which often is that concrete allowing moisture to pass from or through. We need a dead air space, which occurs underneath the floor covering. And then we need food. And if that food is an organic filler or some kind of a paper product in a wall system, we have now a case of health issues that are more important than floor covering issues. The other thing I'm touching on here, and we'll talk more about later, is the high moisture adhesives that are being brought to market that say we can install when concrete in situ relative humidity is 95%, 97%, 99%. They can lead to a very false sense of security. And for the moment, let's just say beware, and we'll talk a little bit more about it later in this package. Resinous floors. I think we've already touched on it again. 100% solids product, hard to soil, hard to stain, but almost impermeable. And once again, we've taken the solvents out because of VOC regulations. Just to share again, because I'm talking to people from California, it's been a bunch of years ago, but I was called to a couple of the smaller airports where people had airplane hangars and they'd had an old epoxy floor that had been down for years and years and years, stained, looked like hell, Skydrol and all the other things that had gotten into it, but it was well bonded. So it was decided to just scratch it up enough so that we could get a new epoxy or polyurethane to stick. That's what they did. 90 days later, that new product, because it was impermeable, shut down the whole system and everything came up with water blisters underneath. People said, what happened? Well, what happened was the result of the newer products. So when I talk about moisture vapor intrusion into a building envelope from or through a concrete slab, and we want to look at its effect on floor covering systems, I try to break it down into some parts. And that's what we're going to talk about. We're going to talk about the source of that moisture. We're going to talk about the resistance to the movement of that moisture from or through the concrete. And then we're going to talk about the drive factors that make this happen. Because without drive, we don't have a problem. It's drive that makes it happen. Now, before we do that, and I'm sure everybody knows these terms, but I always like to touch on them because sometimes they are used interchangeably and they're not. And that's the difference between concrete curing and concrete drying. Concrete cures as a matter of a chemical reaction of the reaction of water hydrating cement particles to create this man-made agglomerate that we call concrete. That's a chemical reaction. Anybody that questions it, go out after concrete's been poured for a couple of hours, touch that concrete and it's hot. It's exothermic, it's giving off heat because it's a chemical reaction that is occurring. Concrete dries by evaporation. And I'm often asked, how dry can concrete actually get? And fully dry concrete will attain an in situ relative humidity matching the ambient. So if the ambient relative humidity is 40% or 50%, the concrete, if suspended and or fully protected by a vapor barrier below, will also attain 40 to 50%. And while we're going to talk about it in the testing portion, this is one of the things that becomes important to me. When somebody has an older slab in an older building, calls me and says that there's an 80% relative humidity in that concrete when the ambient is 30%, that is a red flag screaming to me that there's not an effective vapor retarder under that concrete. So when we talk about moisture analysis, first question is, where does the offending moisture come from and what can be done to control it? So when we talk about moisture sources, the first one that's important is the residual concrete mix water. It takes about 3/10 of a pound of water to hydrate a pound of cement. Now, if that's all we put into our mix, we would have something akin to Play-Doh. We couldn't transport it, we couldn't place it, we couldn't form it, we couldn't finish it. So we add more water, often called water of convenience. Common water cement ratios are maybe a 0.5 to a 0.6. I have seen in California mix ratios higher than 0.6, but recognize that even at a 0.45, we have 50% more water than was needed to hydrate the cement itself. That's the water that's a threat to us. Most of that we want gone if possible. Something that's not often discussed in California is the water in the aggregate. And I've put in here limestone versus granite. The limestone available in California is so porous you cannot put it in concrete. But in parts of the country you can, and we see limestone can hold 3 to 5% of its own weight in moisture, where granite or quartz can only hold about 0.5%. That difference slowly leaches out of the limestone and creates long-term drying problems for concrete in a number of parts of the country, not so much there. The other thing, and we're going to talk more about it, is the use of lightweight aggregate. Lightweight aggregate's typically going to be poured in a pan. That lightweight aggregate cannot be placed in the concrete in a dry state. It has to be pre-saturated. So I have seen situations where, in fact, going back to California, I'm going to try to focus on things I've dealt with there, had one mix design where the batch ticket showed 900 pounds of a particular lightweight aggregate. I called the batch plant and I said, okay, of the 900 pounds of aggregate, what percentage of that is actually water used to create a saturated condition, but not reported? And they said, oh, it's 30%. So this was 270 pounds of water that was not reported in the mix design that was actually in that concrete. And what that means is that it's going to dry very slowly. We're going to talk about that a little more as we go on. So the next place that I'm concerned about is the content of a blotter course if one's used. Now, I don't know that it's still happening, but for years and years and years in California, you would place a vapor retarder on the ground, you put 2 inches of sand over the top of the vapor retarder, and then concrete over the top of the sand. You cannot place concrete on dry sand. And the proof of that is anybody that's gone to the beach, gets out of their car, steps off the boardwalk, steps into dry sand, and you sink into it and the sand displaces. Same thing would happen if you tried to drop concrete onto that dry sand. So it must be pre-wetted. Typically, a geotechnical engineer is going to tell us to take it to 5% to 10% of its own weight in moisture to gain the compaction that we would see at the water's edge if we were walking. Well, if we have a high quality vapor retarder and 2 inches of wet sand, the only place that water can dry slowly is through the concrete. So not only does it mean that we have a long-term drying problem, it's going to mean when we talk about testing that we're testing the moisture content of the concrete, not of the sand. So we have really a bunch of invalid information. ACI and ASTM for years have said, whatever you do, don't use sand under concrete. I don't know that it's still being done, but you need to ask on your projects if they've put in a blotter course and if it's sand, because that is a threat to your floor coverings. ACI, ASTM have always said to use a granular fill if you're going to do anything at all, so that we can gain compaction in a dry state by simply proof rolling it and we don't have to add water. Some parts of the country have been putting rock over the top of vapor retarders. That was not ever done in California. I'm not going to address it, but think about it for a minute. I've seen situations, particularly in the Kansas City area, where they'd tail end drop crusher run rock over the top of vapor retarder and then be absolutely shocked when they found that the vapor retarder was full of 1 billion holes made by the rock that they dropped on it. So when we talk about that moisture in that blotter course, it's either intentionally placed for compaction, as I just said, but it could accidentally be placed by rain. And I have been on a site where we had placed the vapor retarder, we placed a granular fill, in fact, on top of that vapor retarder, but didn't plan on placing concrete till the next day. Well, guess what? It rained overnight. So we're out there, they're placing concrete, they're moving forward anyway. We just grabbed a little paint can top scoop of that granular fill, took it back to the lab, cooked it out, and it was 20% moisture content by weight. And again, that means saturation of that material. That concrete's going to take forever to dry naturally because the granular fill has to dry also. And then when we look at a subslab soil moisture content, you know, our biggest threat there is an ineffective vapor retarder. If we have moisture in the soil, and I promise we do, now we need a vapor retarder to be controlling it. So that's either a native condition, but it can be the result of irrigation, trenching, or plumbing. But those are our sources of moisture. So there's plenty of threat available. And I'd like to point out some of the things that I always find interesting. We talk about this as if it's a relatively new problem. And it really isn't. The first floor covering moisture-related failures that are documented actually go back to the mid-1950s, when we had Levittown and a few others trying to build slab-on-grade homes for the returning vets from World War II and Korea. Lot cheaper to pour a slab than to build a pier and beam foundation. So those failures were occurring. And in 1958, the basically what was the FHA, Federal Housing Authority Administration, excuse me, commissioned some studies by the Academy of Sciences National Research Building Council. And what they basically found was that regardless of where you were in the United States, moisture directly beneath the slab, that we approached 100% relative humidity, even under favorable soil and drainage conditions. So if we've got 100% soil moisture content in the soil, excuse me, I promise you're going to end up with 100% inside that concrete slab. And this again is why when people talk about a 92 or a 95% adhesive, I don't care. If it's an old slab, I know that we can achieve 100% and fail that adhesive. So it's not a good answer if we don't have a high quality vapor retarder directly under the concrete. So when we start talking about controlling moisture, we've talked about all the potential sources. Now, how are we going to create some resistance and try to limit the ability of that moisture to get into that building envelope? And of course, our first concerns are the pre-construction geotechnical considerations, those native conditions. And I've added to this in yellow that geotechnical engineers and plastics. I'm not seeing it as much today. There are GCs on the program, maybe they are. But for a while, I would regularly see an architect as far as what to do about subslab conditions and a vapor retarder. They'd simply put in their specs to see the soils report. And then you go to the soils report, and the soils report would say, hey, there's moisture in the soil and you need a vapor retarder. And that was the end of it. And when I'd talk to some of the geotechs who I got to know, I would ask them, you know, just how much of your training was in plastics? And the answer was, of course, absolutely none. And the reality was they were saying we were simply offering a direction to the architect that he needed to specify a vapor retarder. And the architect was saying, well, you said put one in. So there was no consideration. Now, today we are seeing, and I hope you always see, that vapor retarder is called out as an ASTM E1745 vapor retarder, and it's got to be placed directly under the concrete. So we can also talk about those slab system design elements, and we're going to talk about water cement ratios and curing and some other things, but there are some other ideas that can be considered. I'm not a fan of all the silicate admixtures that are being offered, and we'll touch on that a little later, but I am a fan of products like Aridus, which is an offering from US Concrete out of Texas, but I know they've got people in California that are licensed to work with the Aridus program. Aridus will commit to delivering a self-desiccating concrete that will dry to an internal relative humidity of 80% in 60 days. That takes a lot of problems out of this equation. Again, it's self-desiccating, and really all that's saying is we're going to use superplasticizers and other materials in order to reduce that water cement ratio to as low as possible so that it doesn't take much time to dry. But those are things that we need to be looking at, the elements that are actually in the slab system. Construction practices become important. I hope that I would never see this again, but I've been on sites years ago, not recently, where it was getting towards the end of the day. Concrete finishers wanted to be able to start finishing their concrete. They wanted all the bleed water to disappear. They're out on the slab with a piece of rebar, and they're punching it through the concrete, through the vapor retarder, hoping that bleed water would go out the bottom of the slab so that they could finish the concrete. Well, guess what? We've just completely defeated that vapor retarder. And maybe they got to finish the concrete before dark, but the floors failed later on. And then fast track construction. You know, there's no question, time is money. People want to build as quickly as possible. But regardless of what an architect or a general contractor wants to make happen, concrete is going to dry at a given rate under given conditions. And the fact that we have a fast track timetable doesn't affect the concrete. It doesn't care. So we need to look at the time of what we're doing. And this is where what Eric was really kind of touching on was, if we're going to build that quickly, we better be planning on doing something to mitigate moisture, you know, mechanically with a membrane or something else. The other thing that I think is always worth considering is post-construction trench work. When we look at ASTM E1643, which is the standard for the placement of a vapor retarder, one of the things that's imperative in that standard is that if we do any trench work, we've got to repair the vapor retarder. And often it's not done. I've been on too many buildings where we go in and basically everything is fine, except we have the outline of a trench all the way through the building where the floors are bubbling and failure because we didn't do anything to repair that vapor retarder when we cut the trenches into the concrete. And I'm not saying that's always an easy thing to do, but it is an imperative thing to do. Or again, add that topical mitigation system over the trench work and maybe take it out another 12 inches just to give us a safety factor. So when we talk about that sub-slab moisture control, and I think I said it earlier, that ASTM E1745 was originally published in 1996. At that point, we had a perm rating of 0.3 perms. In 2011, we upgraded that standard so that the permeability on an ASTM E1745 vapor retarder is 0.1 perms. There are 3 classes of vapor retarder, A, B, C. I don't think we need to belabor that too much. The class A, in my opinion, belongs under commercial buildings, anything over 10,000 feet. A B could be a commercial building under 10,000. And in my opinion, a C should be used residentially and never see its way into a commercial building. The companion document, which I should also always see in the specification, is ASTM E1643, which I touched on, is the standard for the installation of that sub-slab vapor retarder. It does require that the vapor retarder either be attached to or go over or under footings. We need to lap and tape all seams. We need to create boots around any plumbing or electrical work that comes through the vapor retarder. And again, we need to repair any trenches. It has to be a contiguous sheet to be effective. So when we talk about then, you know, what do we want to be looking at? When we look at the elements of that concrete itself, here again, this is a 1965 study that was done by Brewer for the Portland Cement Association. And what he found was in a laboratory, not in the field, but in a laboratory, if we had the same aggregate, same sand, same amount of cement, but change the water cement ratio at a 0.40 water cement ratio. And I don't know whether that'll, I guess I can do this. I guess that shows up. The 0.4 water cement ratio, we can actually achieve dryness that would support a floor in 60 days in a laboratory, which we're going to touch on what that really meant. At a 0.5, we start extending that out to where it's about 90 days. Once we get to a 0.6, you know, we're out there at 120 to 180 days. So when somebody wants to talk about fast track construction with a 0.6 water cement ratio, it's not going to happen naturally. We could add mitigation, but it's not going to happen naturally. Another study that I think is important and relevant to the discussion of what we're doing under concrete, and here again, how old is it? 1954 by the Housing and Home Finance Association. They actually made some canisters, and in that canister, which was stainless steel, we had a glass tube that we could monitor water levels inside of a subsoil. We had a stopper filler tube so that we could add water to the model. And then at the top, they actually created 6 models. All had 4 inches of concrete. Some of them had a membrane under the concrete. Some of them had coarse gravel under the concrete. And out of those models, the ones I want to talk about are model number 1, which is what you're looking at. We did have a capillary break made out of gravel. We had a membrane directly under the concrete, and then we had the concrete. And after that concrete had dried, so this was a year-long study, I looked at the data in the last 60 days because that represented moisture passing through this model, not moisture that may have been affected in any other way. But in model number 1, again represented in the picture, we had about 2.5 pounds of vapor emission. Well, guess what? We're looking for 3 pounds or less when we looked at calcium chloride tests. This model, in fact, delivers concrete that would do exactly what we need to do. There was another model where they took out the gravel and the membrane, put the concrete directly on the earth. And in that case, we had a little over 6 pounds of emission. Not a horrible threat, more than most floor coverings can stand, but not a horrible threat. What was most interesting to me is they made a model where they took the membrane out, so it was just concrete over gravel. That model delivered almost 20 pounds of emission. Now, why that was important to me was, again, in California, you see, or I saw a lot of projects where we would have just that, 4 inches of gravel, and then clear plastic as a vapor retarder, and then concrete over that. Well, the clear plastic is basically worthless. And in fact, we were seeing 22 pounds of emission, and most people were saying that's impossible to achieve. Well, when you think about it, what's happening is that that gravel, of course, has airspace around it. And what this really dramatically showed me is that when moisture was in contact with the sand, yeah, we had a problem. But by having a rock capillary break, the airspace around that rock encouraged any moisture that reached that elevation to turn into vapor. And in fact, it's vapor that passes into and through concrete, not liquid water. So if there's going to be a capillary break, and I understand the need based on geotechnical concerns, then a high quality vapor retarder is an absolute necessity, and it must be properly placed. So we touched earlier on that lightweight aggregate, and typically, again, this is what we're going to be pouring up on those metal decks to save weight. And I've argued with architects that, you know, they want the big expanse between columns that lighter weight is allowing, without giving consideration to the fact that the lightweight aggregate means that the concrete's going to dry far more slowly, and they may have a greater cost for mitigating that second floor or third floor deck than they would have spent on just more structural members holding the whole thing up. So to that end, the Portland Cement Association years ago wrote a rule of thumb on concrete drying. And that was that hard rock concrete will dry at the approximate rate of 1 month per inch of thickness. However, that's when the air temperature is at least 70 degrees, maximum ambient relative humidity of 50%, and constant air movement. That's achievable in California. It's not achievable in lots of parts of the country. At the same time, because of the expanded use of lightweight aggregate, it's been only a few years ago that they wrote a second rule of thumb, warning people that if you're going to go to that lightweight aggregate, it's now going to take 2 months per inch of thickness. So if we've got a deck and that deck is 5 inches at the thick area, 3 inches at the shallow area, if we look at the 5-inch thickness, we should anticipate 10 months for that to achieve dryness. That's not going to happen in a schedule, and I know it. But recognize that's the concern we have when lightweight aggregate is placed into that concrete. So we're going to talk about some guidelines that ACI, not the flooring industry, has put together. ACI 302.1R and 2R, one is a guide to concrete floor slab construction. The other is a guide for concrete slabs that receive moisture sensitive flooring materials. And now I'm going to say that virtually every flooring material is moisture sensitive. They're making the warning that if the concrete slab is scheduled to receive a floor covering, moisture sensitive floor covering, it should be directly underlain with a vapor retarder or barrier. And I've put under that warehouse floors. One of the issues that I've seen all across the country is we see developers that are building these office warehouse projects where they'll pre-plan that 5,000 to 8,000 feet of floor space is going to be the office, and they in fact put a vapor retarder under it. Then we have the rest of the building, which might be 10 to 20,000 feet, and it's planned to be a warehouse floor. So nothing is put under it. And too many times we'll see an electronics manufacturer or somebody like that move in. He needs an ESD floor all through the facility. It gets installed. And of course, what happens 90 days later, we have a floor failure in the warehouse area because there's no vapor retarder under that warehouse. So when I have the chance to discuss this with an architect, my opinion is there should be a vapor retarder under the entire slab unless you know the life use of the building and that there will never be a floor covering installed. Because that vapor retarder is pennies a square foot. We already know mitigation is dollars a square foot. This is a value to the owner of that building, even if they don't see it up front. The other thing that I think is important when we're talking to architects or a general contractor, ACI, again, the American Concrete Institute, in their 302.1R booklet, has floor classifications. And there are 9 classifications. I want to focus on just 3 of them. The class 2 is a single course, meaning a single layer of concrete, not multiple layers for whatever reasons, but a single layer of concrete. It's intended to host a covered surface and receive foot traffic. ACI's recommendation is a light steel trowel finish. When we look at a class 4 floor, still single course, exposed or covered surface, foot and light vehicular traffic, then we want a normal steel trowel finish. And it's not until we get to a class 5 floor, single course industrial floor for manufacturing, processing, and warehousing that we want a hard steel trowel finish. That's not what's happening in the world. We're seeing hard steel trowel finish across the floors all over the place. And there's no question that concrete finishers have been sold on the idea of these big ride-on power trowels because it does allow them to hit their FF and FL numbers. But if we hard steel trowel that surface, we are densifying it to the point that we're not allowing it to dry. So they're exacerbating our problem. And I understand their requirement was to meet an FF and FL number and to meet a concrete mix design. They could care less whether this concrete dries, not their problem, not their assignment. But the next guy, the Eric Esparces and all the rest of them, they need dry concrete and it's not going to happen. So when we look at the effect of surface texture and drying, again, that's dense, hard steel trowel finish is going to inhibit drying. It's a great floor for a warehouse. Just as the picture shows, and I'm sure you've all been on site, the concrete actually shines, it's been burnished, but it's not going to dry readily. And in fact, ACI, along with CTL out of Skokie, Illinois, actually created a slab that was so dense that it self-cured. There was no reason to do any curing because they densified it to the point that water couldn't get out. It self-cured. Never dried, but it self-cured. A light broom finish, which arguably is not something most people are going to want as a finished floor, but it will promote drying because there's nothing holding it in. And just to share a quick story, because we do have some GCs on the line, I was invited to a building in Chicago, and basically it was 2 towers with a center that was going to be a reception center. The reception center was intended to have ceramic floor covering versus adhered, resilient, and all the other things in the other two towers. So we sink in situ relative humidity towers in the tests in the towers, and we were very high. We were up in the 90% range, and at that time, we didn't see some of these high humidity adhesives, so we couldn't install a floor. But I got them to allow me to put a couple of in situs into the light broom finished slab, which was the same thickness, same mix design, and we were almost 20 points lower. So there's no question that if we allow the concrete to dry, it will. And I've run into at least one architect on the East Coast who started specifying light broom finish for schools because he said, we are skim coating every slab anyway. I'd rather have one that was dry that we just skim coat rather than one that we're going to skim coat anyway, but now I have to have a mitigation system included. So not suggesting that, he did it. He felt he was successful with it, but it was the point to be made. So, you know, when we again look at then the Division 3 versus Division 9, we have some conflicts. We have, again, often the specification in Division 3 that we want a hard steel trowel finish. We want to meet the FF and FL number, but we're going to have a floor that's not going to be very porous. Then when we look at curing that concrete, we've got to start talking about, well, we're going to do that with a membrane or a cure and seal. Membranes take time to dissipate. Cure and seals are intended not to dissipate, thereby inhibiting or prohibiting drying. So when somebody sends me packages on the Division 3, one of the first things I look at is what has been specified to be the curing compound. And if it's a reactive cure and seal, we can't allow it. The intention of a cure and seal is to hold moisture in the concrete and not to dissipate, not to allow that concrete to dry. Membrane forming curing compounds, we still have two families. We have self-dissipating, breaks down under UV or traffic, and then we have non-dissipating, which are typically thicker acrylics. But even then, while that curing compound, curing system is in place, we are either inhibiting or prohibiting drying. And that has to be recognized because it's not until the curing system is gone that drying starts. So if that curing compound that there's a few of them that I think are reasonable, 1100 clear comes to mind, says right on the data sheet, it will start to break down after 4 weeks. So that's 1 month, no drying. Now we start drying. So if I have a choice from a floor covering standpoint, the best choice is always to cover cure the slab or use a curing blanket. We can wet cure it. I don't know whether that's being done. It used to be done, excuse me, in the Palm Springs area where they'd bound sand around the slab, pond it with water, let it sit for 3 to 5 days, and then let the water off of it, and we had a cured concrete. There are curing blankets that are reusable that I recommend from a number of choices. And here again, we pull the blanket over it, we let it sit 3 to 5 days, whatever our structural says we need, pull the blanket off, we can reuse it, and now drying starts. So we're in control of both the drying process and the curing process. Again, the worst choice is a reactive silicate because it's intended not to go away. The next worst is a non-dissipating membrane. And if we're going to use a membrane forming curing compound, it should be dissipative, must meet ASTM C309 or 1315 specifications. But even in that case, I would prefer that as soon as curing has been reasonably achieved, and I'll leave that to a structural, that we physically remove that curing compound and let drying start. We go to that ACI 302.2R, which was slabs intended to receive moisture sensitive floor coverings. And this is where things start becoming important for everybody that's involved in testing concrete dryness. Their position is, and I agree with completely, a moisture test should not be used to predict the future concrete drying behavior, to provide evidence that moisture criteria are satisfied, or to establish expected floor covering performance if the concrete slab has not been placed directly on a vapor retarder / barrier. I think it's worth jumping in here and defining those two words. The American Concrete Institute has defined a moisture barrier as a material, actually their definition is as a rugged multiply membrane having a perm rating of 0.000. Anything else is a vapor retarder. And that is a warning to us that it's going to pass some small amount of moisture in vapor form. Barriers are typically used, at least in California, for methane issues. I've never seen a barrier placed purely for moisture. We use vapor retarders, and we have wonderful ones. California is the home of Stego. It's a product that's used nationally. I am absolutely a fan of the product. It's a great product. So again, my only caveat in this statement was that they didn't, they just said vapor retarder or barrier, and I'm saying that the vapor retarder got to be effective. So we want an E1745 Class A vapor retarder. I think we've already touched on them, that those standards that I want to see in a specification, the most recent version of ASTM E1745 was written in the year 2017. Those last two digits always tell us when it was published or revised. So that is the standard specification for the vapor retarder under a concrete slab. And then 1643, most recent version is 18, and that is the practice for the installation and inspection of that vapor retarder. And I think we've gone through what's in there. We don't need to rehash it at the moment. What is important to me is to remove the word visqueen from everybody's vocabulary. Visqueen was a wonderful product made by the Visking company up in Chicago. It was typically 40 mils thick. It was used not only under some concrete, but it was also the material used for these plastic sheet covered greenhouses. It was a great product. But visqueen is no longer made in this country. There's a British company that has bought the rights to the name, makes a product that they cannot import to the US. So you should never see visqueen on a box. And really it's a generic term. It's kind of like Kleenex. There are no performance standards attributable to the word and no value to the building owner when visqueen shows up in a construction document. I have gone to construction supply houses and literally played the game of saying, hey, I need a box of visqueen, small job, 2,000 feet, and it comes in a 20 by 100 roll, and out they come out with a box that's labeled construction plastic, doesn't say visqueen anywhere on it, and all it is construction plastic. So my problem then with construction plastic, clear construction plastic, is when we talk to the people who make it, most of them will tell you, and there's only a few anyway, that very often that is made from recycled materials. Those recycled materials are permeable. They will never meet an ASTM standard. So if I take a core from concrete and I see clear plastic is what's on the earth, I basically say there is no vapor retarder. If it doesn't have color, and that's how we tell them, Stego is yellow, Raven is blue, Reef is green. I mean, they're all adding color so that we know what they are and have for years. If it's clear, you cannot trust it as a sub-slab vapor retarder. I do want to touch quickly because there's so much out there of the silicate-based admixtures and topically applied penetrants. Most of these products do not allow testing under ASTM F2170, which is our in situ relative humidity test, or a calcium chloride test, the F1869. They say they don't have to do that and that they've tested their products with ASTM D5084. D5084 is a test intended for soil or rock, and we again can call concrete a man-made agglomerate, man-made rock. but it's actually testing liquid water under pressure against that concrete to determine how much liquid water will pass through the concrete, and then judging permeability based on that. Well, as I tried to point out earlier, concrete by itself does not readily pass liquid water. Our threat is moisture vapor, and D5084 has absolutely nothing to do with moisture vapor. So if somebody's going to look at these products, you're going to have to be happy with the claims they're making, but a floor covering contractor is not going to be allowed to test their products often. And even if he does do the tests, people are going to say, ignore it because we're warranting the whole thing. Well, that's all fine and good until the failure happens. And all too often, and I'm not going to name names, but all too often, when a failure occurs, the first thing I hear is the floor covering contractor did not allow the adhesive to flash off long enough. That's why it is wet underneath the floor covering. And now we have the finger pointing and the arguing as to whether moisture passed out of that silica treated concrete or whether the floor covering contractor actually did what he was supposed to do. So it just becomes ugly. I don't like seeing silicates. To that extent, and to take it a step further, XL Brands, which is a large floor covering adhesive manufacturer, they sell under their own label, but they also private label for a number of resilient manufacturers. And they, since 2014, have had this position on their website, that they will not warrant their products over any substrate containing reactive silicates, whether it's entrained or topically applied. So you need to be aware of that when somebody wants to bring you that silicate product as an answer to moisture problems. What I try to get flooring contractors to do when they're faced with that is to ask for a waiver against moisture. I tell them you will go out with every combination of adhesive and product that you're due to install. Make sure that initially we get bond with those products. If we don't get bond, shut it down right now. But even if we do get bond, recognize that some of the problems, and as alluded to in this statement, it's the latent bond failure that becomes problematic. So we need a waiver against latent bond failure if we in fact have done bond testing that we've documented upfront to show that there was adhesive bond when we put the floor in. Real quick touching, and I know we're getting past the hour or so that we were allotted, just some of the ASTM floor covering related standards. We're not going to go into testing today. We're going to do that at another time. But ASTM F710, latest version 2019, this is where we see the baseline for dryness of concrete at the 3 pounds per 1,000 feet for 24 hours under a calcium chloride test, 75% in situ on an RH test. And of course, we also have our pH testing in F710. Calcium chloride test is ASTM F1869. The in situ relative humidity test, ASTM F2170. I've used the word preferred because virtually all resilient manufacturers are now requiring that test. There are even some manufacturers that ignore calcium chloride results. They want to see that in situ relative humidity test. I still use an electronic meter as a secondary piece of data. There is an ASTM standard for that, ASTM F2659. I like to point out, because I occasionally see ASTM E1907 show up in a specification. That's an outdated guide that was written by the E6 committee, not the F6 committee. So it's outdated and has no value. And then I still see the plastic sheet test show up, ASTM D4263. There's just not enough information from that plastic sheet test to tell us anything about the suitability of that concrete for floor covering installation today. Testing equipment, again, not going to go into testing per se, but you know, we want to test concrete and determine whether it's moist or not. I'm going to go back here for a minute because I'm going to focus on it in the next seminar. But the testing that you're looking at, all of it, is premised on testing original concrete placed over a vapor retarder, and we're testing the condition of that new concrete. These tests were really never intended for use on older concrete. We use them on a daily basis, but we need to condition that information with knowing whether there's a vapor retarder or not. And that's critically important, because without that vapor retarder, this data is truly a picture in time, which we hear a lot of people say. It truly is a picture in time. It's subject to change without notice. If we have a high quality vapor retarder under that slab and we see test data, unless that floor is flooded or a sprinkler breaks or something else, it can only get drier. It cannot get wetter. If it's not on a vapor retarder, it can get wetter. It's also important when GCs are in the room, and for the flooring contractors that are sitting there, that our testing be done in an acclimated environment. And that's not always easy to do. And I understand that. I get calls all the time. Can you come out and test the concrete? Sure, I can come out and test the concrete. I had one here in Arkansas. We had a cold winter. And I said, what's the temperature in your building? And they said, it's 40 degrees. I said, okay, it's going to cost you $2,500 to test the concrete. I'll do it. And in my report, I'll tell you the data is worthless. Now, do you really want me to do that? And then we talk about the need for an acclimated building and why it's important that we have one. So it is important for all testing. It is absolutely critical if you're going to do a calcium chloride test. And I will touch on that a little bit, and that's kind of, then we'll open it up to questions. But this is where drive comes from. And that's what I was alluding to in the beginning. The vapor pressure differential between the concrete and the building envelope is what is our drive. So the highlighted numbers that we have here, if we take soil under a building, except that it's 100% relative humidity, and assume that it has a 65-degree temperature in the soil, if we're asked to go out and test, and you've got about 75 degrees in the building, and in California, you likely wouldn't have 70% relative humidity, but you could if it had recently rained and it was damp inside the building. We have a very low difference between these numbers, okay? Once we button up that building and have 70-degree temperature and maybe 40% relative humidity, our static vapor pressure drops to 0.145 pounds per square inch. And now we have a dramatic variance, and it's that variance that sucks moisture into the building envelope. Nature is always trying to equilibrate the amount of moisture in the soil against the amount of moisture in the concrete against the amount of moisture that's in the airspace. So if our concrete is wetter than our air, which it typically is going to be during a drying process, the drive factor, the vapor pressure, is what's going to make that happen. So testing in an environment that doesn't match service conditions is going to give us misleading data. So I'm going to, at this point, open that up to questions or concerns. I think we've covered a ton of information very quickly, and again, would hope that I haven't scared anybody. Oh, you know, I do want to touch on, because Eric mentioned desert floors, and why did floors fail out in the desert? Anybody that takes a desert survival class, I have a son that was a Navy pilot. He actually took that class. We talked about it. If you'll take a desert survival class, you'll be taught that if you're in the desert and have no water, the way to achieve drinking water is to dig a hole about 3 feet deep, about 2 feet around, put a cup in the middle of the bottom of the hole, cover it with a bedroll liner or whatever you have with you that may be plastic, seal the edges of that plastic on the top surface with sand, and drop a stone in the middle of the plastic. within 24 hours, there will be drinking water in that cup. There's enough moisture vapor in the sand that will condense when we cross dew point overnight, and it will drip into the cup. You'll have drinking water. I promise. If you can do that, you can fail a floor, and we do it on a regular basis.
Hey, thank you very much, George. That was a lot of information. I'd like to open it up to questions. I would imagine there's a few out there. Anybody?
Yeah, George, so you're basically just letting me know that we're pretty well screwed in most of our jobs.
Rick, I was looking at your face the whole time, just like, I don't know how you get a project done.
I was thinking about jumping off, but I don't think it would help. But the problem we have, of course, you touched a little bit on it. We have a soils report that says whatever it says. You have an architect that says what they're going to say in their spec book that they use constantly. All they do is print it and change names. And then we have sometimes a structural engineer that gets involved. So at the end of the day, they just say, well, read the fine print. It's up to you guys. You know, it's your problem. And so I think, let's just say, for example, that I may have a project that used the Stego, right? Great stuff. But it had 4 inches of sand on top of the Stego.
Correct.
What's the chances? And then there's a curing compound, which I don't know what it was, what we use. I mean, I could find out, but I don't know today.
Right.
So we have all these things that I think are causing us, going to cause us issues. And what's the chances of that concrete slab curing? And we went through a winter, or not much, well, it's California, but still, you know, it's not hot. It's not conditioned space. We can't get Edison turned on. So what's the chances of that concrete being cured?
Okay, so I'm going to be rude, but I don't
That's
mean
okay.
to be rude.
Go ahead.
I'm going to take the word away from you. You asked, what's the chance of it being cured?
Mhm.
Excellent chance of it being cured.
Okay.
And it has been cured, but it isn't dry.
Okay.
And so that's the difference between curing and drying. Curing
Okay.
takes all the water we can throw at it. Drying means the evacuation of water we didn't use for curing.
Okay.
And, you know, the chance of it being dry, it is almost nil within a year or two.
Okay.
Yeah. And this, you know, California has the benefit of having ambient relative humidity very often as low as 20%. I've actually measured it in Beaumont, for example, ambient relative humidity of 5%. That really causes drying, no question about it. And it's worth noting here when I'm talking to a general contractor, one of the reasons calcium chloride tests have fallen out of favor is just that condition. When we look at how concrete dries, it actually dries on a curve. And if we have, here again, just as you said, if I've got 4 inches of wet sand under the concrete, and then I've got concrete, and then I've got 5% ambient relative humidity, the surface of my concrete is going to be dry. Well, a calcium chloride test only looks at the top 1/4 to 1/2 inch of concrete. That's going to report that as dry concrete. We install a floor, it fails, we come back, do another calcium chloride test. Now it's 10, 12 pounds of moisture. Everybody says, what changed? Well, what changed was that moisture infiltrated the concrete, saturated out the concrete, and now we have a huge problem. So not knowing how much water was added to that sand,
Right.
hang on a sec. Let me, I wasn't planning on doing this, but that's okay. I did at one time, and I think I still have in my notebook here, the calculations, because I don't want to make it up. Oh, come on, where is it? Where is it? Maybe I don't. I apologize. But I took, you know, if we take sand, which weighs probably about 120 pounds per cubic foot, let's call it 100 for the moment, and let's take it to 10% moisture content. So that's 10 pounds of water per cubic foot. So if we're going to slice that cubic foot into 4-inch wafers, if you will, we're going to cover 3 square feet with that cubic foot of sand at 10% moisture content. So in 1,000 square feet, we have roughly 333 cubic feet of sand covering that 1,000 feet underneath the concrete, 10% moisture content. We just came up with 3,300 pounds of water per 1,000 feet of concrete that is ultimately got to dry through that concrete. It's a huge amount of water.
Okay. All right.
Hey, George. This is Andy Nelson. I'm the maintenance manager for San Bernardino County Superintendent of Schools. Eric invited us to this because we've had some fun issues with moisture mitigation as well. So my first question, and this is going to be a simple, stupid question, is I'm dealing with already as-built, so they're already done. So how would I go about finding out if, assuming we have DSA, which is a really strict building requirement stuff, but still, I could swear that I have a few school sites that don't have moisture barriers. I could swear by it, but and we of course have inspectors and everything else. But how would I go about finding out if it actually does or did have a moisture barrier?
Yeah, and if it's not in your drawings and plans, which very often it is, and I've seen even old plans that clearly show that there is no vapor retarder or call out visqueen. And if they call out visqueen, I guarantee you it's clear plastic. Forget about it. It is worthless. You may as well consider not having one. If you need to know, and if there is a question, then the size I like, I take 6-inch cores. Take a 6-inch core out of the concrete. That gives us enough room to get our hand in there. We can hand excavate and just physically look, see if there's a vapor retarder.
Okay.
But again, let's talk about other ways that we can red flag something. If we start with the premise that concrete will dry to the ambient if allowed to, and if fully protected by a vapor retarder, that means if you've got an older school in San Bernardino and I do an in situ relative humidity test, I should expect to find relative humidity in that concrete down in the 50 to 60% range. If it's higher than that, that's a red flag. It's telling us there really isn't one. And if you have a relatively permeable floor in place and you're going to replace it with an impermeable floor, now we're going to talk, as we did earlier, the difference between, so moisture that was at least partially passing through our old floor is now completely inhibited from passing, and we're going to build to that 100%, and we're going to fail that floor.
Yeah, we've had some issues with, we switched one from being an old broadloom carpet to a VCT, and all of a sudden we had all sorts of fun stuff.
Absolutely, not uncommon, sadly.
Yeah. So my last question is this: we actually have a building that was built. It's only about six or 7 years old, and so I have no moisture issues except for where the concrete slabs are seamed together. So I have this perfect line down the middle of my hallway where the slab. So I have no doubts that they probably put some sort of moisture barrier down. But where the slabs are actually seamed together is where it's obvious. I mean, I got bubbling up on my tile, and this is a new, well, it's like I said, 6 to 7 years old.
Right. So my first thought, without knowing any more, is that we have a cold joint, as you're saying. We have 2 pores that are set together. We have a cold joint, goes all the way through the concrete. Likely you have a sand blotter course underneath that slab. During construction, it likely rained on that concrete. Well, what happened then was where the concrete was solid, well, we're okay. But where there's basically a crack going all the way through, water ran all the way through, went into that sand layer, which was a sponge to hold it. And now over some period of years, you're going to end up suffering the results. So my first thought in remediation would be we need an epoxy type filler in that joint And then we need that remediation system to probably go a foot or two on either side of that joint. And if there's no other problems with the slab, you would likely get away with it. I would still want to see more data before you committed to it, but it could work.
Yeah,
So you wouldn't need to do the entire floor of moisture mitigation, George?
Again, I would want to see more in situ data to make me feel comfortable with that.
Okay.
But if we have the anecdotal evidence of a problem limited to an area, recognize that moisture cannot move laterally through concrete. It moves vertically, but not laterally more than a couple of inches. So any water that went down that joint, assuming for the moment that I'm correct, any water that went down that joint is only going to move by capillary action the distance it can in the sand, again, once our vapor pressure differentials are overtaken by the forces of capillary action and just the forces of the water, it's not going to move any further. And that's why I'm saying potentially, if we just sealed on either side of that joint by a couple of feet, we may get away with it. So as long as, again, we're trusting a vapor retarders under the whole thing, so this isn't an intrusion, this is something that happened from the surface. And I mean, you're just reminding me, I was called up to Bakersfield to look at a similar situation years ago. They were building a new section of a hospital. They ran out of money, so the slab sat for a year under the weather and exactly the same condition. Everywhere there was a cold joint, and in some cases where there was a saw cut that had cracked through, we had problems. The rest of it was fine.
Okay, that's great. Thank you. Appreciate that.
That's really good.
Because Eric is coming your way, just so you know. Another.
Yeah. It's like the Chino one, right? It's similar to the Chino.
Yeah, exactly. Except for Chino, the acid moisture coming up through from the cow fields.
I was going to say, when you build over cow pastures, I've cored concrete that sat on cow pastures with a vapor retarder, and this literally happened. We took the core out and carefully dug down by hand, and the vapor retarder was literally dust. That was all that was left. It was completely eaten.
Oh, interesting. Okay.
Yeah, so it wouldn't even matter if they put the moisture vapor down, because it was built right on old cow
Yes.
dust.
Yeah,
Mhm.
I don't know that would happen with the polyolefin products like Stego, I don't think would be attacked, but the polypropylene products that were used had been attacked and destroyed.
So, hey, George, so I just want to recap. So you're basically saying it's 1 month for the concrete, 1 month per inch for the concrete to dry.
When it's allowed to dry. If it's got a curing compound and it's not allowed to dry, that 1 month per inch starts when it's allowed to dry.
Oh, so when the curing compound is done.
Yeah.
Okay. So we're talking 4 to 6 months for a slab to dry just without the curing compound factor. And then on the second floor, lightweight concrete, you're talking 8 to 10 months?
Potentially. Now, we can speed that up. You know, there are ways to speed it up by reducing water cement ratios and et cetera. But as a rule of thumb, as a place to start talking, that's the place we start talking.
And so, okay, what about this then? So this, and also sort of like a steel finish. So as a flooring contractor, as my reps go out there, we should be concerned about any of those steel finish flooring, because we're concerned that the water didn't have a chance to escape.
Yep, absolutely. If we hard steel trowel the finish, we are going to, again, diminish the ability to dry. And it's a sad situation. And I think what Rick was alluding to was, but there's all these parties, and Rick, you're absolutely correct. That's why I and other people like me offer these seminars. I do them for architects, general contractors, flooring contractors, building owners and managers. Education is the key to stopping this.
Yeah. All right, so then if I were an estimator at a flooring contractor, George, then I should be looking in Division 3 and checking to see what the cure and seal product is.
I agree.
Just to make sure I'm not screwed later on.
I would agree. Or I would offer, and I do this for a number of Fuse members. You're a Fuse member. You know, they just send me the Division 3 and say, is there something I need to worry about? And I'll go in and look for, you know, how is it intended to be finished? What are we using for a curing compound? See if there's anything in there that is potentially threatening. And then, you know, we want an RFI going back in saying, guys, you know, we can live with this, but there's a good chance you're going to pay for either an upgraded adhesive or a remediation system when we're talking new construct. Again, if it's remodel, first thing I do is ask for the age of the building. Second thing I do is ask, has there been any trench work done in this remodel? Because if there's been trench work, we can go look to see if there's a vapor retarder and what it is. So we don't even have to do a lot of investigation. It's going to be there right there in front of us.
Springs, A and D.
Hey, George, what out of all the top coats and epoxies you've seen out there, what have you seen that have been the most effective?
And to say a specific company, there are a number of them. Here again, ASTM Committee F6, which I sit on, wrote a standard for the practice of using epoxy mitigation systems. It's ASTM F3010. Anything that meets that standard is going to work. So whether it's Ardex, Mapei, Coaster, oh gosh, there's a number of them anymore that are very effective. If I have any criticism for some of the products that have come to market, some of them are claiming you don't have to do any surface prep and their product will magically stick. And I'm here to tell you that if we have residual curing compounds or some other contaminant, no, we need a CSP3 before we're going to trust the effectiveness of the bond of that epoxy.
I should take it to a CSP1, but you don't have to.
George, do you see any issue with when you put that epoxy down, maybe sprinkling very light, and I'm talking just maybe a few granulars, you know, every maybe 10 grams the size of a dime down just to get some adhesion, better adhesion and so forth?
Okay, as far as the sand broadcast?
Yeah.
Yeah. You know, some of them require it. I did work for Floor Seal Technology for 4 years before I opened my business. So we did exactly that, applied epoxies. And when you see a manufacturer or a remediation system manufacturer that wants you to use sand, it's because he doesn't trust your ability to time an installation. If you put the sand in, you will get that bond. So I'm not going to argue that. But what I'll also tell you is that if you have a one coat system, if you get into that system with cement before final cure, but after you're able to walk on it, so this is a timing issue and it takes some expertise, you never needed to prime it. It's only after the epoxy has cured that you're going to need to prime it to get something to stick. And so again, if we threw sand in it, you don't need to be worried about the primer. So it's more a timing issue. I don't have any problem with the sand other than typically when you look at somebody that requires sand, it is sand broadcast to refusal, which means complete saturation. And then after it has cured, you sweep off the rest. That's just a lot of work.
Yeah, it makes a mess. Yeah. Okay.
George, I got a question. How should we test the floor if we cannot confirm if there is in fact a vapor retarder below? I know you mentioned doing coring to look for that vapor barrier, but that'd be a lot of work in a lot of these quick TIs. That's just not very realistic. You'd mentioned if there is no vapor retarder, our testing equipment wasn't really designed for that. Is it still trustworthy to do the traditional results, not knowing for the back there's a vapor barrier or
Okay,
retarder?
so here again, this takes a little investigation on your part. So let's talk about concrete just a little bit. Concrete is going to pass moisture if it can. So if we had a floor covering in place of any kind, there is going to have been some restriction to that passage of moisture. So the first thing I want to do, if I'm going to be on a project where it's being remodeled and there has been a floor covering in place, I want to test where the least permeable floor was. So if it was sheet vinyl or VCT, that's where I want to test. I don't care so much about where there was broadloom carpet. I do care about where there was resilient. And if I do a test in those places, and that test shows me a 75, 80, 85% relative humidity, I don't need a core. I know there's not an effective vapor retarder. Otherwise, that concrete would have to be drier. So the concern comes when you're testing like a warehouse floor that's never hosted a floor covering. I'll give you an example. I've done work around the country at commissaries for the military through an architect here in Arkansas that does them. And we had one out Fort Benning, 100,000 foot facility, 50,000 was warehouse, 50,000 was occupied space. They're going to do a remodel and they're going to expand out into the warehouse. So we tested where there was tile in place. And then we also tested out in the warehouse where there was no floor. In the occupied space, we were running between 80 and 85% relative humidity, just as I'm talking about. So it screamed that there was not an effective vapor retarder. In the area that was warehouse, where there had been no floor covering, we were down in the 60% range. Now, if I relied on that data, I would end up with a floor failure because I already know that the adjoining concrete placed at the same time in the same way was capable of taking on moisture. There was not an effective vapor retarder under that slab. And if we put a less permeable floor down, the moisture content in the concrete would only increase. So again, it's playing detective a little bit and analyzing what was there at the time or before you did your test and add that information into what you're looking at.
Thank you. I actually have one more question too, if you could elaborate a little more. You mentioned how moisture moves vertically, not laterally. We've seen some tests or some jobs where the majority of the slab throughout the whole entire flooring plan was below 70 or 80%, but we get one test and say it was in the middle of the slab at high 90s. Are you saying then we could mitigate just that one room in that area and not have to mitigate the entire slab?
The potential answer is yes. Okay. And you know, it would always be good to know why you saw what you saw, which isn't necessarily your responsibility. It would often be the responsibility of somebody else. But it can be for any number of reasons. It could be that the vapor retarder was seamed where you're having a high reading and it wasn't taped, it wasn't overlapped, it was just kind of brought together and it's really wide open. I've actually also had to, I'm just thinking back, things that relate to what you're saying. We had a situation in a residence where we had just one area that was exceedingly wet and wood floor was failing, discolored horribly. We ended up coring the concrete, and where the bulk of the home was 4.5 inches, this was 1.5 inches. So the real problem was that there really wasn't any concrete. So there are typically reasons for what we see. And again, I don't think as a floor covering contractor, it's your responsibility to learn all that. It would be your responsibility to report it potentially to a GC. And from an interest standpoint, be part of the investigation. I would agree with that, but you shouldn't have to. However, your original question was, if we have one high reading and a bunch of good readings, do we have to treat the entire slab? The answer is no.
Thank you, Rick. Oh, sorry. Thank you, George.
Ah,
Yeah. All right.
Any other questions out there? I don't think so. Hey, thanks so much, George. Thank you, Rick, Andrew, Doug, and those of us who joined us in person. I appreciate your attendance. Again, we're having the moisture testing in 2 weeks. We'll have another seminar with George, testing and remediation. He'll go through some of the different test methods, why they work, why they don't work, and also he'll kind of go through, touch on the different remediation options and how they can be used and how they'll work.
Yeah. Please conclude me. Thank you.
Yeah, thank you very much, Doug. Everybody have a good day.
Thank you. Nice meeting everyone. Thanks, George.
thank you.
Hey, thanks, George.
Ah, my pleasure. You guys have a good day. Take care.
Okay, take it easy.
Ah.
Do a better job of marketing than that. I think that one's good, though. They don't know shit. Rick Jackson was like, Rick Jackson was just, yeah, I'm all right. We're basic stuff. They can't solve that. Yeah, they can't solve that Toyota standard, right? Yeah. You know what I mean? They're like, no, we're only on that fucking floor. We're not touching that. You need to look at every division field and the field and also what you're saying. No, you're reading it, you're figuring out if a part cell finish and they're using a reactor filling kit, then you need to send an email to the project manager or the VP and say, you have a moisture problem with this. No, the exterior seal doesn't allow the water to come out. To dissipate. And the hard shell doesn't allow the water to come out. So does the reactor silicate steering seal. ground and just put away the part in there that mentioned that, soak it, but it also, it doesn't dissipate. So the water stays there. So you need to send an email to a contractor or a division. So they're basically saying in 3 months, in 6 months, 8 months, when we go out there and test for moisture, it's going to come high. So plan on putting a change order, plan on putting some money towards moisture. Because the way you design the building, you're fucking. You're fucking stuff. Yeah, or just take on facilities. Or change the drink on that. Yeah, does that make sense? So now we have to look at it. But now you're skin cover. Correct. Oh, they realize it. I thought it was different. The manufacturers would prefer to make their food, have a food, that manufacturers. Yeah, the industry's still pretty small. There's not a lot of guys like George Donald talking about this. There's only 2 people, 3 people talking about this. And even George Donald is not that great at it. You know what I mean? Yeah. He's not that great at it. So yeah, no. So it's inform us. And George Donald, I mean, real big. No, you know what I mean? Like, I believe the things he's saying. Yeah. I got it. Is that ready? Yeah, I'm off to Colorado. Good deal. I'm available. I'm working. Thursday and Friday. Right. Yeah. No, it don't sound like you sound to me. I didn't like the way Fuck, Michael, where's the fucking key?